Well, my quantum journey continues. Last week, I believe I described verbally the photoelectric effect. I saw an MIT a lecture in which they actually did the experiment. I don't have platinum or zinc on hand and ultraviolet light and all those things, but I thought I would at least take this week and talk a little bit about what that experiment might look like. So let's dive right in and do Einstein's photoelectric effect. So a tale of two frequencies. We're going to hypothetically shine radiation on some platinum. I decided to do platinum. Why not? The chemical abbreviation for platinum is PT, not physical therapy or physical training, but PT, platinum. Tale of two frequencies. So what we're going to do is we're going to use platinum as our metal, and remember each metal, platinum, zinc, etc., each metal has a threshold energy. This is the amount of energy where if you're below that energy, no electrons are going to go dancing. But if you get above that energy, then yay, it's electron dance. And that threshold energy is sometimes called the work function, which is a strange name for it. I think we're stuck with it. It's what it takes for it to work. It's the work function. Look, it's functioning. It's working. But it's really the threshold energy it takes. And that EV stands for electron volts. And electron volts, when we're talking in this area, are within a fairly low range of 0 to 10 kind of counting numbers. I can handle counting numbers. So the threshold energy for platinum, and this is fixed for each metal, right? The threshold energy above which the electrons dance is 5.65 electron volts. Now, we can figure out what this is in terms of frequency. Remember, that's a nu, not a V. And so remember, E equals h nu. And so if we divide both sides by h, which is Planck's constant, we get the frequency equals the energy divided by Planck's constant, which turns out for platinum, therefore, to be about 1.37 times 10 to the 15th hertz. That's a pretty high frequency, right? Okay, so this is what we need. We need, if in energy, we need this amount of electron volts, or in frequency, we need this high of a frequency in order for the electrons to dance off of a platinum surface, to go bing, like out of a hot pan. Get out of here, get out of here. For the electrons to jump off the platinum surface, you're going to need that frequency or that threshold energy. Okay, so the setup is we need a platinum plate, not a eating plate, but anyway, we're going to need a platinum plate. And again, we could have used another plate, a zinc plate. And then we need a radiation source. We're going to have two hypothetical radiation sources, one in the infrared, which is not going to work, and one in the ultraviolet range, which is going to work. So we're going to need to have two radiation sources and some sort of a frequency meter to tell us where they're at in terms of their frequency. And then we're going to need an electron detector to see whether the electrons dance. Let's dance and jump off the platinum surface. All right, frequency number one, red laser pointer, and this is what they used. I looked for other infrared sources, but this is the one that seems to work the best. And this is what they used in the MIT lesson that I was watching. So, red laser pointer. Okay, frequency number one, the frequency of a red laser pointer is about 4.62 times 10 to the 14th hertz. So let's figure out what the energy that's going to come off of such a pointer is. Well, Planck's constant is 4.14 times 10 to the negative 15th electron volt seconds. By the way, you might be saying, I thought it was a 6.6 number, like negative 34 or something like that. And you would be right, but that's in joule seconds. So for this particular video, we're not doing joule seconds, we're doing electron volt seconds. So it's just a different unit of energy. So this is what Planck's constant is in electron volt seconds as opposed to joule seconds. So we're going to take that 4.14 times 10 to the negative 15th, and we're going to multiply it by this frequency of the red laser pointer, giving us 1.9 electron volts. Not going to happen. No electrons danced. Sorry, you get a door prize as you go out the door. The red laser pointer not working. Infrared too low. Remember, what are we looking for? We're looking for about a 5.65 electron volt. So the 1.9 is too low. Womp womp. Okay, well, our next contestant in the photoelectric effect is right is a UV lamp. And so let's pick a UV lamp with a frequency at 1.62 times 10 to the 15th hertz. This is a fairly dangerous to your eyes UV level. I forget the number of nanometers the wavelength is. It was something like 100 and it's 100 something. It's a dangerous frequency to look at. Let's say it hurts your eyes. Do not look at this lamp. This is used for oxygen purification or water purification, I think, ozone creation, that kind of thing. But so this is a fairly high frequency UV lamp. So let's figure out what the energy using this lamp is. Planck's constant again, 4.14 times 10 to the negative 15th. Electron volt seconds. Sorry, that should be electron volt seconds. There, I feel much better. Electron volt seconds times 1.62 times 10 to the 15th hertz. And the winner is, drum roll please. Taking a long time. There it is, 6.7 electron volts. Ding! We have a winner. The electrons dance. Jump off your platinum and dance. Okay, so the photoelectric effect is demonstrated here, even though no platinum was used, no ultraviolet light was shown, or infrared light. But this has been another step in my quantum journey. Schrodinger's course. Does it exist? Does it not exist? I don't know. Let's open the box someday. Have a great Saturday.